and welcome back. We are well within our e-learning. The world is starting to open up, and life is good. Welcome back to the chemistry classroom, I guess you can call this. We have what 2, 3 more weeks, and we are done with this semester, done with this year, and hopefully done with this whole e-learning full-time nonsense. But in the meantime, let's go ahead and get started on the project and what we're doing today. What we're doing today is going to be relate very, very closely to what we did last week. Now, if you remember, because some of you work ahead, some of you work behind, just a quick reminder that what we worked with last week was the freezing point depression of something. Now, a couple people had questions. Just a quick reminder, freezing point and melting point are the same point. So those questions where I was asking it for the melting point, it's the exact same thing, because whenever something freezes at, that's also the temperature that it melts at. So let's go ahead and get to work here and get to our boiling point depression. Before we get to that, we need to talk about something called electrolytes. Now, electrolytes, you probably heard this word a lot, and honestly, you probably didn't know what they were talking about. If you watch almost any food commercial, especially for sports drinks or anything like that, you'll probably hear them saying, "Oh, electrolytes this," or "You need electrolytes," or whatever. Well, what electrolytes actually are is they're any substance that dissolves in water to give a solution the ability to conduct electric current. Now, if we were in person and being able to actually see that, we would set up a solution of purified water and a solution of just regular water with salt in it. And we would try to conduct electric current with it. And you would see that purified water, aka water that is just H2O, nothing in it, does not conduct electricity. It doesn't conduct it almost at all. Now, in theory, it shouldn't conduct it at all. It'll conduct it a little bit just because it's very, very hard to get 100% pure water. But what happens is when you add ionic solutions or add ionic compounds to water, they become electrolytes, which start conducting electricity. It becomes the partial charges on these ions that dissolve in the water, they dissociate from each other, that allow electricity to flow through the water so that it actually can conduct electricity. So, an electrolyte is used by only ionic compounds. So there are covalent compounds that can sometimes mimic this effect. They are not electrolytes. So things like sugar, all that stuff, that is actually not electrolytes. Back when they were first starting to develop Gatorade, their main goal was actually to help athletes get their electrolytes really high. That way, it can help conduct electricity better in the body, which allows the body to work better. If you actually tasted the original version of Gatorade, the one that was developed in Florida for the Gators, you would probably vomit. It was not good. It tasted horrible. It was mostly salt. It was basically straight salt water with a little bit of sugar so that they could actually drink it. So what happened is that they found that salt's a very good electrolyte, and they put it in. There's actually a solution for a homemade Gatorade the World Health Organization gives out to all the people who are in impoverished countries who can't afford things like Gatorade. For a 5-gallon bucket, you take a fistful of sugar, a pinch of salt, and something else I can't remember off the top of my head, and you put it in, you mix it up, and that will give all the people in your house enough electrolytes so that you can keep functioning throughout the day, even in hotter climates where that kind of thing isn't normally there. So electrolytes are super important. Make sure you get electrolytes when you're working your stuff, but make sure that you know what they are. They're very important. So Electrolytes, they're created by dissolving or dissociating an ionic compound in a solution. In order to conduct electric current, ions need to be able to freely move in a solution, meaning that salt, regular table salt, will not conduct electricity by itself. It has to be in this solution to actually conduct electricity. So, like I said, we're going to be dealing with boiling point elevation. So, solutions of water will not only freeze at a lower temperature, they actually boil at different temperatures as well. They boil at higher temperatures. So, the greater the concentration of a water solution is, the higher the boiling temperature. Now, here's a point that I know a lot of you are going to try to contest me about, because, like, well, someone told me this. Well, someone's probably wrong. When you are making pasta and you put in salt to the water to help it boil faster, that is not correct. That's not why you do that. It actually makes it take longer to boil. Salt, being an electrolyte, actually raises the boiling point of the water, making it so that it takes longer to boil. You do that for taste, only for taste, not anything to do with time, boiling point, or anything like that. You put salt in there so that it helps your pasta taste a little bit better. Not anything to do with time and boiling point. So, we have almost the exact same equation. When I say almost, I mean literally we changed out F's for B's. Which, let's hope we can do that with all the grades. Going from F's to B's, pretty good. So, the only difference is that you're going to be using the boiling point constant and add the change to 100. So, we have boiling point elevation amount, a delta TB, so change in boiling point, plus is equal to boiling point elevation constant, which for water is always given to us as 0.512 degrees Celsius per molality, times molality of the solution times Van Hoff's constant. So this is the exact same equation. The only difference is we're dealing with boiling point, not freezing or melting point. So let's go ahead and do a couple practice problems with this so that we all know what we're doing. So what would the freezing point be for a 2.2 mole solution of NaCl and water? So we're dealing with freezing point right now. We're not doing boiling point, so let's look at freezing point. We have our freezing point equation as delta Tf equal to KFMI. So let's look at what we have. We're looking for this. We're looking for the change in the freezing point. We're given Kf as 1.86 degrees Celsius for molality. We're told molality is equal to 2.2 molal. And then we need to find I. I is the Van Hoff's constant. Now I walked you through how to find that, but we're going to go through it again. We look at NaCl. Is NaCl an ionic compound or a covalent compound? You should be answering ionic compound. If you don't remember how to do that, you look to see if it's a metal and a non-metal. For this one, we have the metal of sodium and the non-metal of chlorine put together, so that means it's an ionic compound. So, because it's an ionic compound, we have to add how many atoms are in this compound. So if I look, I have 1 atom of sodium for every 1 atom of chlorine. Because of that, it's just a simple 1 plus 1, because there's 1 atom of each, gives us 2. So we have 1.86 times 2.2 times 2. Then all you gotta do is put that into your calculator, and you will get 8.184 degrees Celsius. Now, important point to make, and I may not have made this abundantly clear last week, this is the change. That's what that delta means. It's the change in the freezing point. So, for this, all we gotta do is we take the original freezing point of water, which is 0. It's the original freezing point of water. Now, we need to see, are we going down with this number, or is the change going to be a negative or a positive? For the freezing point depression, it's going to go down. So that means we have to subtract 8.184 degrees Celsius, which equals negative 8.18 degrees Celsius. That's all that is to it. It's a very, very simple little equation, very, very easy to do. So, we're going to do this multiple times. I hope it will be a little bit easier. Okay, so we did a freezing point depression. Let's do a boiling point elevation. So a mixture of sugar and water has a molality of 5.6. What's the boiling point be for this solution? So we're dealing with our new equation, which is almost exactly the same as the old equation. Which is delta TB is equal to KBMI. So let's go ahead and plug and chug. We are looking for the difference in boiling point. So we're looking for delta TB. We have KB given to us. If you don't remember what KB is, I'm just going to look right up here. KB is 0.512 degrees Celsius per molality. Then we have the molality, or M, which is 5.6 molal. And then we need the Van Hoff's constant. So the Van Hoff's constant, all we got to do is look at the solute, which is not water, so it's going to be sugar. Very good. So sugar, is sugar covalent or ionic? All of you should be saying covalent. Any covalent compound, anything that's not bonded with a metal and a non-metal, has a Van Hoff's constant of 1. So all we really have is 5.6 times 0.512, which gives us change in 2.8672, which we're going to say is the change in the boiling point. Now, if this is the change in the boiling point, what's the actual boiling point going to be? Well, this is going to be a boiling point elevation. So we're going to elevate it from what it was previously. So when does water boil? 100. So 100 plus 2.8672, so 100 and 2.867. Now we got to look at what we're given. We're given 5.6. We're just going to go ahead and call it an even 103 degrees Celsius. So it's not that bad. Okay, final one. A mixture of magnesium chloride and water has a boiling point of 115 degrees Celsius. What is the molality of this solution? So we're not asked for this now. We're going to be asked for this. So I'm going to go ahead and get M by itself. I have delta TB is equal to KBMI. This is being multiplied, so the easiest way to get things that are being multiplied is divide them. So we have the change in the temperature. If it's 115, 115 minus 100 is 15 degrees Celsius, divided by KB, which is 0.512, times I. I for magnesium chloride is magnesium is 1, chlorine is 2, 1 plus 2 is 3. So if you plug all that into your calculator, you should get that it is 9.76 molal. That should be with sig figs.